Okay, so the next talk is from Nikola Stoilov from the Université de Bourgogne, and he's going to talk about numerical studies of the Davies-Stewardson and Zakharov-Kuznetsov equations.
Hello, thank you very much for the kind invitation. I am very sorry that I cannot see you all in person, but hopefully next year. So today I'm going to tell you about some works on Davies-Stewardson and Zakharov-Kuznetsov equation, one non-integrable system that we have studied numerically, and I will emphasize the difference between the two systems. So this talk is based on joint works with Svetlana Roudenko, who is in International University of Florida, Ken McLaughlin, who is in Colorado, Christian Klein and Johannes Jostrand, who are here in my colleagues here in Dijon. So there will be a very brief introduction due to the small format of the talks. I will just say things about how we do numerics, as this is somewhat more specific. Then I will explain how we address some PDE problems about Davies-Stewardson equation, namely its critical behavior. And then also discuss Davies-Stewardson as an integrable system, namely I will look at a numerical approach to the inverse scattering problem. And then I'll move on to the Zakharov-Kuznetsov equation in 2 and 3 dimensions. So we're interested in solving partial differential equations, generally evolutionary ones. So numerically, what we do is approximate the solution on a numerical grid, which reduces the system of the PDE, so the system of PDEs, to a system of coupled ODEs, and then this can be resolved with standard ODE methods, although for very large matrices. There are, generally speaking, 3 flavors of spatial differentiation. One is finite differences or finite element methods. So this is essentially using local polynomials of low order. So I look at the functions locally and I approximate them locally with in different manner in different places. Finite volume methods is more or less the same, but they use expansions in local expansions in functions that are smooth. Spectral methods were the latest to arrive. This uses approximations in globally defined smooth functions. The most famous one of them is the fast Fourier transformation. The largest challenge on working with spectral methods is that first, they work very well if the domains on simple geometric domains. So if you manage to put your boundary conditions to be coordinate surfaces, and second, they are not very well scalable in the sense that, in the following sense, they require so the differentiation can be expressed through a differentiation matrix, and in the case of spectral methods, the differentiation matrix is always full, so always dense. This is in contrast with the local methods, where the differentiation matrix is of usually 3 diagonal, 5 diagonal, or something like this. So it is linear with the number of collocation points. In the spectral method, it is quadratic, which, if you're playing with millions of billions or tens of billions of points, is a significant difference. The first major success was achieved by Orszag in '71 when he discussed orthomorph instability. Periodic problems are resolved well by the Fourier series with fast Fourier transformation. The advantage here is that due to the fast Fourier transformation, differentiation is not of order n squared, sorry, but of order n log n due to the Kulitöki algorithm. If we have Schwarzian functions, they can be considered as periodic for sufficiently large domains with 0 boundary conditions. The advantage that we get is that we get exponential decrease of the error. This can be traced by looking at the Fourier coefficients, and it's called spectral convergence, which means that with several thousand points, we can achieve a machine precision if everything is going okay. If it is not going okay, then we may need more power. For non-periodic problems, I'm not going to, no, I'm actually going to discuss about this today. We are using polynomial interpolation, so we separate the computational domain in several subdomains. One of them may contain the infinity point, and then we use globally defined functions into these domains to achieve spectral precision with appropriate boundary conditions on the passing of domains. So the first thing that I would like to discuss is David-Stewart's equation and its critical behavior. Critical behavior in this case means we start with regular initial data, and in a finite time, there is a singularity. This is also called a blow. So the starting point is the nonlinear Schrodinger equation in one dimension. This is a universal equation, describes evolution of slowly varying wave packets, and finds applications in nonlinear optical fibers, Bose-Einstein condensates, gravity waves, and plasma models. This particular NRS equation is integrable. There is an inverse scattering method for it. The David-Stewartson is a two-dimensional integrable generalization of the nonlinear Schrodinger equation. So we have 2 dimensions as every higher dimensional integrable equation, it is non-local. In this case, it is written as a local equation. However, if you invert for phi, the equation becomes non-local. This model physically describes interaction of long and short waves, and there are various integrable models. So depending on the size of the factors in the equation, we can distinguish several types of DS. Now, there is a large amount of partial differential equation results on the behavior of NOS and particularly critical behavior. And the idea of how it works is to look for scaling invariance. So we have a scaling transformation for a certain, not this generalized nonlinear Schrodinger equation, for certain values of the nonlinearity and the dimension, there is a criticality of the L2 norm, and this leads to existence of blow-up solutions, because I can make the height the solution very tall and compress it into space. In the 1+1 dimension, the critical nonlinearity is 4. This is called the quintic NOS. In 2+1 dimension, the critical nonlinearity is the quadratic one. So in some cases, DS is suggested to have a blow-up. Now, in order to, so the mechanics of this is you can make the rescaling dynamic. So we introduce a scaling factor that depends on time. And this allows to study a blow-up in focusing NOS analytically, at least for cases with generic blow-up in one point. And one can obtain the rule for how do norms behave. So if you consider the rescaling factor, then what you can see, and this you can see numerically, are the norms, the behavior of the norms. So what we're looking at is these two power factors there. So David-Stewartson is critical in this sense. In 2+1 dimensions, the hyperbolic NOS, this is the David-Stewartson that we are looking at without non-locality, has a focusing and defocusing direction. And the intuition tells us that there will be no blow-up there, because if the equation is focusing in one direction, then it will disperse in the other. Now, because DS is an integral equation, we know exact solutions, and one of these solutions is so-called Tozawa solution. So what Tozawa did is take a standard lump. This is the two-dimensional sort of soliton that is slowly decaying for the DS equation. Apply pseudo-conformal transformation, and thanks to this pseudo-conformal transformation, we obtain a solution that explicitly blows up in one point in time, which can be set up by the parameters A and B. So, because this is an analytic solution, it sort of exists after the blow-up. which we cannot see numerically, but the analytic solution exists before, so before the time of the blow-up and after the time of the blow-up. And now the interesting point was that the blow-up rates that you obtain via the Uzawa solution are not the ones that you would expect from LS. So the question that we wanted answered is Uzawa solution somehow special? So is this because of some strange mechanics that this particular exact solution has these blow-up rates, or this is generic? And our conjecture is that all the that actually this is the generic behavior. There is a formula with which we found for the conjecture rather numerically for the scaling factor, and also we have found that the profile, so the shape of the blow-up shortly before the blow-up happens, is that of a scaled lump. So we know at what pace the blow-up happens and what is the shape of the blow-up profile shortly before the blow-up. Now, the problem with the Uzawa solution and with all this is, and why do we need spectral methods essentially, is that you start with a highly oscillatory initial condition. And if you do not correctly track the high oscillations, for which you need either Fourier or somehow spectral polynomial methods, then you cannot go very far because then the solution is very quickly lost. So this is how the infinity norm of the real part of the Uzawa solution. So it has high oscillations in the beginning around t equal to 0, then the oscillations smoothen out and all the mass goes into the peak. So this is now the numerical experiment that we are able to do. So on the left we track the infinity norm. So this is how fast does the solution blow up. And by fitting this curve, we found out that this behavior is the prescribed one, and this is a local plot which explicitly gives you how much is the value of that fitted rational function there. Now I'm showing you this. So this is a numerical run on an explicit solution. So I know how much is the solution. But it is important for several things. First of all, it shows that at some point I lose precision. So I have a numerical method that is very precise, but there is I'm getting close to a singular point. So the numerical method stops working. So it loses the solution. And I can establish these points by looking at the conservation of mass and energy and at the spectral coefficients of the solution. So I can judge both the spectral resolution that the spatial resolution that I have and the temporal one, and these are two separate things. And on the right, we see that also that the P-off point where we lose the solution is clear. And the important part here is we have obtained the same behavior for Gaussian deformed lumps, and generally speaking, data that is hump-like in general position. So this we have rich numerical evidence for this this conjecture. However, there is no analytic proof. So this is somehow an invitation for the analytic community to look at this and try to find a proof. Although in 2+1 dimensions, this is always difficult. Now, the second thing that I would like to tell you about is that David-Wilson can be treated as an integrable system. The equivalent of Riemann-Hilbert problem for multidimensional system, in particular for DS, is played by what is called the system of D-bar equations. So we have these two equations with auxiliary functions, psi1, psi2, which are now called complex geometric optic solutions because of their asymptotic conditions. And if you look at that, you immediately see that at infinity, you have an oscillating singularity, which is not great for numerical methods. So we needed to somehow more advanced approach. There is a reflection coefficient. So this is the dual variable somehow from, I have the potential Q. I can find the reflection coefficient, and then the evolution of the evolution flow of ds is given by this simple evolution flow of the reflection coefficient. Now the inverse transform, so this was the direct transform. The inverse transform is also given by a system of dBar equations replacing Q and R and vice versa, and then the asymptotic conditions have to be taken with respect to K, not with respect to Z. So the focusing case is more problematic in this case. So all our numerical considerations for the defocusing case, the sigma can be entered as a parameter and we can deal with this. However, there may not be any solution. So this we have not looked at if whatever we compute is actually the split or something like this. And there may be exceptional points. So this needs careful analytic work before you can deploy the, or more careful analytic work before deploying the potentials. For Schwarzian potentials, the dBar system goes to a singular equation in the Fourier space, and the trick that we did is to compute the singularities explicitly. So we have an analytic approach to peel off the singularities, compute them separately up to numerical precision, so up to 16 orders of magnitude, plug them back in, compute everything else numerically, and we find solutions with very high precision. So the second class of potentials that we looked at is potentials with compact support of the disk. In this case, we look at, we use compactification of external domains with Chebyshev methods. Actually, in some cases, this is simple enough that you can also only work in the disk and then deal with the external part analytically. But this is not always so. The problem here is that we get a highly oscillating factor. So we have these equations, and when K gets very high, it is very difficult to compute. For this reason, we, with Johanna Sjöstrand, looked at asymptotic behavior. So we actually have an improvement of this formula in, we have two joint papers, so that we can compute analytically with the expansion around h equal to 0, so also very large curves up until around 1000, we can obtain a precision of 15 orders of magnitude with the analytic formula, and below that we can compute explicitly, which in the zone that is unreachable for the asymptotic analysis. So this is the large time behavior, and this just shows the fact that this formula is correct. So this is the solution, and we have multiplied it by K, and it looks almost exactly the same. This is the same for phi 2. Here it is less clear that things are proportional. If you look very carefully there, you see that this section oscillates very highly oscillating region. So this is quite challenging to compute. So a brief application of this, there is diagnostics method that is not very popular. It's called electrical impedance tomography, where the purpose is to measure, to recover the image of a body from measurements of the voltage on the boundary versus the current density for sufficiently many patterns. And it turns out that this boils down to solving a dBar equation, which we can do very well. Here is a picture of how this works in practice. So their current is going out from one electrode going into another, and there we measure the voltage distribution around the chest of a patient. So the second thing that I would like to talk about is the Zakharov-Kuznetsov equation. It was derived as a physical model for 3 dimensions with a fixed nonlinearity. We look at a more general setting. This describes the propagation of ionic acoustic waves in uniformly magnetized plasmas. There was rigorous results later on that I'm not going to stop on. So this is integrable only in the case of KdV and time KdV when it is one-dimensional and the nonlinearity is 2 or 3. There are conserved quantities that we can track. There is a traveling wave solution, so we call it Q. It is, you can consider it a soliton. It goes only in the positive x direction. So these look like lumps, but move only to the right in x. There is again scaling invariance, and we can, in the two-dimensional case, consider three cases. So subcritical case where there is no blow-up, critical case that when there will be a blow-up for sufficiently large mass, and supercritical case where there will be a blow-up for essentially any mass. There are two models, algebraic dependence CFL and exponential dependence in L. So we can again track norms. The conjecture that we have is that that case, the soliton is orbitally stable, and from general initial data, which is sufficiently smooth, the solution will decompose eventually into solitons and radiation. So solitons are stable. So I start with, I deform slightly the soliton, and then let it propagate to the left, to the right. And it stabilizes at a higher value. Here, because I'm in a moving frame of reference, the soliton that started fast, that became larger is faster, so it is moving to the right. This one is slower, so it is staying on the left. So now we looked at soliton interactions, and this is the classical thing that you know from KDV. But this is a non-integrable equation, so there is significant difference. So this is a picture that we have all seen, and this is the faster soliton overtaking the slower soliton. And what we know in KDV is that there is a phase shift. The faster soliton moves slightly further away, but they keep their profiles and their speeds. This is no longer the case in ZK. So the soliton which was at the back, the faster soliton, is accelerated, so it becomes taller, gets more mass. The retarding soliton is slowed down even more and is smaller. And this is a zoom out on the part of the computational domain which is sufficiently far away from the pure soliton. So the pure soliton is exponentially decaying. So somewhere they should be zero, but there is radiation throughout the entire domain after the interaction. There are soliton interactions in which two solitons merge. So I start with two small solitons. I produce one large one, and some radiation, which, if this is sufficiently large, may produce more solitons. Then this is a wall, so I take soliton, stretch it out in the y direction, see what happens. Again, this is resolved, and there is an interesting result about the profile of the radiation that I'm going to talk about in a minute. Blow-up behavior is as expected. So in the critical case, there is a blow-up with the correct blow-up rate. And there is a conjecture about this. The profile close to the blow-up point is a scaled soliton, which we cannot produce with quite a high. So fitting a soliton shows precision of the difference is less than 1% between what we see minus the fitted soliton. So the last thing that I want to talk about is ZK in 3 dimensions. I think I have 5 more minutes because I started late. So we're going to look at soliton stability, interaction, and resolution. Blow-up is something that we're currently working on because it requires fairly high precision, or rather resolution, and our new computer system is not completely ready yet. So there is a theorem by Svetlana and her collaborators. This is analytical results. There is orbital stability and convergence trajectories. So general comp data will decompose into a soliton and radiation, and the solitons are stable. And now the interesting thing is, I'll just briefly say this, when this happens, so you start with an initial lump and you produce a soliton, then asymptotically, so sufficiently far away, the radiation behind it is confined into a zone that opens at pi/3. So we're going to look at soliton interactions. Now, there are 2 types of plots. On the left, I have a section. So again, this is a 3-dimensional soliton. So on the left, I have sections to the maximum value of the function. On the right, I have a color map. The color map is absolute, as we're going to see. So red means that the value is high, blue means that the value is low. So this shows that the solitons are stable and just proves it. And we see, so at the end, we fit a soliton. So we have this solution, which was led to evolve. There is some radiation here, which you may be able to see. This is a plot of the difference between a fitted soliton positioned in where my solution is and the solution, and you see what is the difference. So this is essentially the pure radiation without the soliton. Now we have soliton interaction. The first one is head-on collision. Now what you can notice here is that the red is actually the red that is somehow around 7 or 8, not the red at 9, because the color map is absolute. So this is just a flip picture. The solitons interact and the larger one escapes, and now it is properly at its maximum value. So the outgoing soliton is higher and faster and bigger than the incoming soliton. So this tracks the infinity norm of the entire solution, which means that it tracks the faster soliton. So from there is this shift shows that the solitons change speed. This is the twin soliton interaction. So this, I start with 2 solitons that are close enough to interact. Again, they are exponentially decaying, so they have to actually overlap visibly, and they produce a single soliton. So this is somehow soliton fusion. Again, we start with 2 low speed solitons. We end up with 1 high speed soliton. Now the radiation part is, we look at the Gaussian. So this is what we expect, is that this is going to produce a soliton plus some radiation, which it indeed does. And here is a general, sorry about the spelling of radiation, the general view. So these are hand plotted lines. They are not somehow computed, or rather they're computed, but they are not analytic result. The analytic result is symptotic. So these lines match it though. So the opening of the radiation cone is exactly where as much as it should be. And because we are working with Fourier here, the radiation re-enters the domain, so we cannot really go very far and study proper symptotics. So this shows that if you have a single hump, that this phenomenon, the closing of the cone, happens quite early. This is the soliton resolution. So we start with Gaussian initial data and produce a soliton. This is the difference. So notice that this goes to 0.5. The soliton is of order of 10. So the radiation is small and the fit is quite good. Now the interesting thing is you can have, in order to have a soliton resolution, you have to have not only sufficient mass, you also have to have localized solution. So the Lorentzian initial data that we considered, I call this super Lorentzian, but you have quite large polynomial. So x to the power 20 in the denominator. So this is quite localized, but not exponentially so. This just decays into, notice the changing scale on the left. So it starts at 6, the next one is 2. So this just decays into radiation. And on the right, I can track the infinity norm, so the height of the solution. I start at 20, which for sufficiently compact data will be plenty enough, and it just decays into radiation. So this is the conjecture, and the new thing is that if you have sufficiently localized data for which we don't have exactly analytical result, the solution will decompose into solitons and radiation. If you take a flat Lorentzian, so somehow there is a small flat thing on top, then it will produce a soliton. So that's it. The outlook is to adapt. So in some cases, multi-domain spectral approaches can handle certain situations better, but not all. So you may be able to handle the radiation if you send it into an infinite domain, rather than trying to deal with it. We would like to study multi-hump initial data to see if we can have blow up in multiple points. We have some results about this in studying KDV line solitons in ZK. we would like to understand lower regularity functions. So develop spectral methods that can handle jumps by, for example, dynamic domain allocation. This is important in if you want the breaking down problem, but also in our application in dealing with boundaries in this electric impedance tomography. There is a new time integration techniques that with matching exponential integrators and so on, which are specifically developed for nonlinear equations, which we would like to adopt as time stepping schemes. And finally, we would like to develop a practical computational approach and demonstrator for electric impedance tomography. That's it. Thank you very much.
Thank you very much. So, are there any questions? You can either use the chat or unmute yourself. So, may I ask something, if you don't mind?
Yeah.
If you can go back, like to your final slide.
This one.
Yes, thanks. So when you're talking about a demonstrator for electric impedance tomography,
yeah,
how do you actually mean to use these numerical simulation and these numerical techniques for tomography?
So this is what is called solving the Dirichlet-Neumann problem. So you start with, sorry, this is quite a way back, but the idea is, so what you get is a voltage and current. So you inject current and you create, this is called Dirichlet-Neumann map. So you know for each Dirichlet boundary condition, what is the respective Neumann boundary condition. Mm-hmm. So this means that I have to have every possible pattern I have to have. In practice, it is sufficient that you have a functional basis. So, for example, you apply the current in sine shape around the chest or something like this, and for each frequency of the sine shape, spatial frequency of the sine shape, you get what is the voltage. So then you get information that is called the Dirichlet-Neumann map. Now, because this is a linear problem, you can use green functions techniques. So and then write the integral version of this, which is called the Lippmann-Schwinger equation. Then you use integration by path essentially to move from the potential to the boundary information, and this generates a D-bar problem. So what we can do very well is solve this D-bar problem.
Oh, okay, I see.
Once you measure, you know, there are a large number of problems before that of well-posedness, regularization, actual measurements, finite size of electrodes, and all these things. What we can do well is actually solve the part with the D-bar problem, and we can do it quite well.
I see. Thank you very much.
You're welcome.
Any other questions?